Hello everyone and welcome to another tutorial on Turbomole and its graphical user interface TmoleX. In this tutorial, we'll be working with some 2D materials and employing density functional theory calculations with two-dimensional periodic boundary conditions. As an example, we'll be calculating the adsorption energy of a water molecule on the hexagonal boron nitride monolayer. Based on literature, there are two configurations in which the water molecule can adsorb on the hBN monolayer. The first is where the water molecule is on top of the nitrogen atom with the water molecule in a sort of an erect or upright orientation. And the second one is where the water molecule is on top of the boron atom with the water molecule in a more or less flat or planar orientation. This paper also shows that based on density functional theory with PBE functional, the adsorption over the N atom is more favorable. So we'll be considering that configuration for this tutorial. The adsorption energy is calculated using this formula. We first calculate the energy of the total periodic system with the water molecule adsorbed on the hBN monolayer, and then subtract the energy of the individual components, that is the energy of the periodic hBN monolayer and the energy of the water molecule. Note, we should use the optimized structures for all the energy calculations in the given formula. For this tutorial, I have already optimized these structures, but for the sake of completeness, I will still show the complete procedure. Unlike plane wave codes like VASP, we can use DFT with 2D periodic boundary conditions for the calculation of water and hBN system as well as the hBN monolayer, while for the water molecule, we will perform a molecular density functional theory calculation. Now, since we need the energies of the optimized structures, let's start by optimizing the hBN monolayer. Head over to TmoleX and create a new project by the name of hBN 2D periodic. Next, we click on import coordinate file to import the structure of hBN monolayer. You could use a zip file for this, but for this tutorial, I have already optimized the structure and have the coord file for that over here. Note, I have provided the coord files used in this tutorial in the description down below. You can see that the hBN system has 32 atoms. It is actually a 4x4 supercell of the hBN monolayer unit cell. You can visualize it by opening the 3D molecule builder. The pink atoms are boron and the blue atoms are nitrogen. Currently, no cell is being shown as we need to add the periodic details manually. To do that, click on the periodic button. Now, the most important thing is to enable periodic boundary conditions by changing the periodicity from 0-dimensional to 2-dimensional for our 2D material. You can see that TmoleX automatically tries to add a cell, but the cell parameters are all wrong. Since I have optimized it already, I will input the optimized cell parameters. Since we only have 2D periodic boundary conditions, I only need to enter A, B, and gamma cell parameters. Now, if I press enter, the cell gets updated and you can see that it fits the monolayer perfectly. Let's close the molecule builder and click on continue. Now, although it is usually recommended to use POB basis sets for periodic systems, we will use the def2 basis set for this tutorial, as the POB basis set can lead to a significant basis set superposition error, also known as BSSE. Click on continue again and generate the initial guess molecular orbitals for the system. All the orbitals are doubly occupied as it is a closed shell system. Now click on continue to come to the methods tab. We will use the DFT with PBC. For the exchange correlation functional, let us choose PBE and let's use a grid size of M5. We won't use dispersion corrections for this tutorial, but it can be useful for adsorption energy calculations. Now let's enable the K-point mesh and use a 1x1 grid, which amounts to using the gamma point sampling. Ideally, the number of K-points should be converged. We won't use smearing as that is only needed for metals. Let's stick to the default parameters for SCF convergence for this tutorial. However, for production runs, one may want to use a stricter convergence threshold for energy. Then let's select the universal auxiliary basis set for all the atoms for the density fitting or resolution of identity approximation. Click on continue and select the geometry optimization of the ground state. The default convergence criteria are usually good enough, but in order to accelerate the tutorial, I will reduce the convergence threshold to 1e-5 for energies. I will also enable the optimize cell parameters checkbox Finally, I will run the job. Since this is a large system, it will take some time to run on my MacBook, and therefore the two windows below will not update quickly enough. But one way to still monitor the job is to right-click on the job and open the shell. Then type in ls to see the various files in the job directory. Open the job.las file using the cat command to see the output corresponding to the first geometry optimization step. I will quickly go over the key components of the output file. It contains the header, atomic coordinates, cell parameters in atomic units, fractional coordinates, basis set information, k-point information, and so on. Finally, to see the last few lines of the file as it keeps getting updated, use the tail -f space job.las command. Now you can see that the first SCF iteration has begun. I will now fast forward the video to the end of the optimization. Since I already used the optimized structures, the optimization ended in just 3 cycles. Now we have the final energy for the adsorption energy calculation. Now let's optimize the geometry of the water molecule. Once again, click on File and go to New Project, name it Water, click on Import Coordinate File and import the coord file for water, which I have already optimized for this tutorial. You can see the 3 atoms of the water molecule here. You can also visualize it by opening the molecule builder. Now click on Continue to assign the basis set. It is important to use the same basis set for all the systems, so we use def2tzvp. Then we click on Continue and generate the start molecular orbitals guess. Next we specify the DFT settings. We should use the same settings for all the systems, so I set the exchange correlation functional to PBE. We'll use the same SCF convergence criterion and set the auxiliary basis set to universal. Finally, we click on Continue and then run the ground state geometry optimization. This geometry optimization will finish quite quickly as it is a small molecule. Notice it converged in just 2 cycles as I already used an optimized geometry. You can download the file from the description down below. Note down the total energy for the adsorption energy calculation. Next, we will perform the geometry optimization for the water molecule adsorbed on hBN system. Create a new project with the name water hBN 2D periodic and import the coord file. You can download the file I'm using from the description down below. You'll notice that this time we have 35 atoms, where 32 atoms are from hBN and 3 are from the water molecule. You can visualize these by opening the molecule builder. Currently there is no periodicity information. Go to the periodic tab to set the periodicity to 2D and also specify the cell parameters A, B and gamma. We'll use the optimized parameters of the hBN monolayer. The remaining procedure is the same as the hBN system, so I'll fast forward through it. Unlike the case for hBN, we won't optimize the cell parameters as we want those to be the same as those of hBN monolayer. Finally, we click on Run and wait for the job to finish to get the energy of the total water plus hBN system. You can see that the optimization finished in just 3 steps as I was using the already optimized geometry. We'll note the total energy and plug all the energies we obtained so far in the formula to get the adsorption energy. We get an adsorption energy of negative 0.00439 hartrees. The negative sign indicates that the adsorption is favorable or exothermic. If we convert it to millielectron volts, we get a value of negative 119 millielectron volts, which is higher than the value in the literature because of the basis set superposition error or BSSE. After mitigating BSSE using counterpoise correction, I got a value of negative 45 millielectron volts, which is an excellent agreement with the plane wave value, which is also negative 45 millielectron volts. You can watch this video to learn how you can apply BSSE correction to the adsorption energy calculations. So that is it. In this tutorial, I showed you how to calculate the adsorption energy of a water molecule on the hBN monolayer using DFT with 2D periodic boundary conditions with the help of Turbomole and TmoleX. If you have any questions or doubts, you can leave them in the comment section down below. If you like this video, then don't forget to hit the like button and subscribe to the channel for more videos like these. Thanks for watching and see you next time.